In this video, we're going to take a look at another curve sketching example. So the first thing we're going to do is we're going to identify the X and Y intercepts. We will find the x-intercepts by setting 0 equal to our function. All right, so our function value is equal to 0, and solve that. We find that x is equal to 0. So you have an x-intercept at 0, 0. Notice that would also be then the y-intercept. So when you plug in 0, you'll get our y-intercept is 0. So the xy-intercept is at 0, 0. Next, we want to think about the domain. So we ask ourselves, are there any values that would cause problems here? So we would have problems if we have 0 in the denominator. We also have a square root, so anything that would cause us to have a negative under the square root would also be problematic. We have x squared plus 2, so we're never going to get a negative under that square root. Also, we'll never get 0 under that square root. And so our domain is all real numbers. So our domain is all real numbers. That tells us then there are no points of discontinuity. It is going to be continuous everywhere. So we can go on and try to find our intervals of increase and decreasing by looking at our derivative. So we have low x squared plus 2 to the 1/2 d high minus high d low d high minus high d low squared plus 2 to the negative 1/2 square the bottom, and away we go. So that square root being squared, got rid of that. Here, I'm going to go through and multiply the top and bottom by x squared plus 2 to the 1/2. So now we'll have x squared plus 2 to the 3/2 on bottom. And then on top, when we multiply through by an x squared plus 2 to the 1/2, we'll have an x squared plus 2 on this first piece right here. And on this piece, that x squared plus 2 to the 1/2 will cancel out with that. And so then we'll have just minus an x squared. So we have 2 over x squared plus 2 to the 3/2. So that is our derivative. We want to think about what values would make this derivative 0 or not exist. And that denominator is always going to be positive and larger than 0. So we're never going to get anywhere where this is 0 or does not exist. This derivative, f prime, is positive everywhere. Because it's positive everywhere, f is increasing on the interval from negative infinity to infinity. Perfect. So next we want to think about our second derivative, intervals of concavity. So we saw on our previous page that our derivative was 2 over x squared plus 2 to the 3/2. So if we were to take our second derivative, we will get negative 3 x squared plus 2 to the 1/2 times 2x. Oh, not to the 1/2, to the negative 5/2. Whew. Yeah, so what I'm doing is I'm thinking about this as 2 times x squared plus 2 to the negative 3/2. So I brought the power down and subtract 1 from the power. And so we get negative 6x over x squared plus 2 to the positive 5/2. We notice that our second derivative is 0 when x is 0. So when we look at this sign chart for our second derivative, we're going to break it up at 0, so from negative infinity to 0, and from 0 to infinity. Plug in something smaller than 0, and we will get a positive output. Plug in something larger than 0, and we get a negative output. So f is concave up on negative infinity to 0, and f is concave down on 0 to infinity. Right at 0, we will have an inflection point that was in the domain. So we have an inflection point our inflection point when we plug in an x value of 0 into the original function, we'll get an output, a y value of 0. So 0, 0 is an inflection point. And we have our intervals of concavity. And then let's look at the end behavior. So the limit as x approaches infinity of x over the square root of x squared plus 2 is equal to the limit as x approaches infinity. So we can factor out an x on top, factor out a square root of x squared on bottom, this square root of x squared is just x itself. Well, for values of x that are positive, it's just x itself. And so those cancel, and so we get 1 over 1, or 1. Now, if we were to take a look at the limit as x approaches negative infinity, then we have the x times. So it feels like this work is going to be identical, except something that I kind of glossed over up above is, so there, when we take the square root of x squared, it is x provided the x value is positive. But if the x value is negative, when you take the square root of x squared, you have the negative of that negative value. And so this is x times 1. We should still have a limit because I have not evaluated it yet. So we have x times 1 on top, but on bottom, the square root of x squared, when we have negative x values, it is going to be a negative x. So then that x cancels with that, but we still have that negative sign right there. And so our limit here is 1 over negative 1, or negative 1. So we have horizontal asymptotes. y equals 1, and y equals -1. All right, so let's put it all together. So we have our graph at 0, 0. We had a point. The domain included all values. We have our function is always increasing. So it's increasing from here to here, right? So forever. When we are looking at our end behavior, at -1 and +1, we have some horizontal asymptotes. And we were concave up from -infinity to 0. At 0, we turned and we started being concave down. And that is our curve. All right, come on back for another example where we're going to look at more curve sketching. We'll see you there.